Complex logs and exponents 60 years ago versus the unwinding number. Table 1 lists four properties of the real logarithm where a is real, x and y are positive. So multipliers become exponents. Log of a product is the sum of the logs. Log of the quotient is the difference of the logs. And log and e to the x are inverse functions. But as soon as you get into a complex variables course, these laws no longer are valid. So you got to deal with the uh, principal logarithm defined here, log of the absolute value plus I, and this is the principal argument, and the principal argument lies in the interval open minus pi to pi closed. Well, where did I first find this stuff? About 60 years ago, I was studying my first complex variables course. The text was this book by Panizzi. It's since come out with a second edition. So I'm an undergraduate studying out of this book. And what I found is a very difficult to remember tableau of adjustments that you have to make to the laws of logarithms. And that's what I knew. And when I wrote my advanced engineering math book in 2001, that's what I knew, and that's what I wrote. And it ended up in my ebook version until I just recently updated the ebook version to take into account this notion of the unwinding number. Now, if you look at this paper that proclaims the unwinding number here, 1996, all I can say is I wish I had read the paper and digested it sooner, because it sat in my stack of papers that I'm going to take a longer look at. And it was only recently that I took that longer look. And if you want a copy of the paper, you can download it from this link. So what am I going to do in this webinar today? I'm going to take a look at that messy, difficult to remember and implement tableau. And I'm going to contrast that with this approach from the winding number or the unwinding number, and then do some examples just to show the difference and to see what the unwinding number contributes to this discussion. So let's take a look at the old versus the new. We begin with a definition of this unwinding number. It's defined via this equation. Log of e to the z is z plus this adjustment. And the adjustment is a multiple of 2 pi I times this integer. So k of z is an integer. This symbol stands for the greatest integer less than or equal to the argument. In Maple, this is done with the for function, and this is the imaginary part of. And I'm going to use examples to illustrate this. And this table that you see in front of you, on the left we have the old way, and on the right we have the new way, and that's what I'm going to contrast. So here on the left we have the tableau that I extracted from this 1963 undergraduate textbook that I studied out of. These first four laws are the adjusted laws that one learns in elementary calculus or elementary pre-calculus. Log of e to z is z with this adjustment factor. Log of z to the w, exponent comes out front, plus this adjustment factor. Log of a product is the sum of the logs plus this adjustment factor. Log of a quotient, difference of the logs, you have this adjustment factor. Notice N1 here, and N2 here, and N3 here, and N4 here, and look below at what these functions are. You have N1, N2, N3, and 4. They're all different. So you've got 4 different things to keep track of, and you also have to keep track of when you use them. And here are 3 additional laws of logarithms that change in the complex plane. A product raised to the w, can you distribute the exponents? Only if you put in this adjustment factor. This adjustment factor contains n3. You have a quotient. Can you distribute this exponent? Yes, if you include this adjustment factor. That adjustment factor includes n4. If you have z to the v, and that's all raised to the w, can you multiply these two exponents? Only if you include this adjustment factor, and that's got an n2. So not only do you have to remember these four functions, you have to remember when they apply. So what do these laws look like if you use this unwinding number? Well, here are the first four that parallel what you learned in an elementary course. Log of u to the z is z plus an adjustment. The adjustment is the unwinding number times 2 pi I. Log of z to the w, does the exponent come down? Yes. Here's the adjustment. Notice that the adjustment uses the same function k. The argument's different, but it uses the same function k. Log of a product is the sum of the logs with this adjustment. What does the adjustment use? It's the same unwinding number function k. Just the argument changes. For the log of a quotient, different to the logs, the adjustment has k of this argument, different to the logs. For these three laws, essentially they deal with exponents. Product to the w, does the w distribute? Yes, if you have this adjustment, but look at what the adjustment is. E to the, so forth, and there's just k up in there. You got to know what the argument is. Quotient raised to the w, does it distribute? Yes, with this adjustment. And it's e with stuff and k. It's the same function, just the argument slightly different. Z to the v raised to the w, do the exponents multiply? Yes, here's the adjustment factor. Adjustment factor is an exponential, and it uses k. There's only one function to remember. It is this function. And surprise, surprise, this function k is n1. It's exactly the same as n1. Now, the paper that Corless and Jeffries wrote mentions that functions similar to k appear in the literature. And he specifically mentions that this one cognate of k is briefly considered in Apostle's mathematical analysis. Well, I've got that book in my library, and I looked it up, and it turns out that it's Panisi's N3. So this 1974 text in mathematical analysis, the cognate of k happens to be N3. So I think that this tableau on the right is far simpler because it only involves one function, and all you have to remember is what is the argument of that function for the various laws. Now, since we want to make use of Maple to explore some of these laws, here are the Maple equivalents of some of this 2D math notation. The greatest integer function is floor if you're typing a command. Now, the argument in Maple is spelled out argument, and typically in a book you will see arg. So I aliased arg to argument. Then principal logarithm ln. In Maple, capital I is used for the imaginary unit. You can change that, and I did. You can see here I've used lowercase I because it looks more natural. RE for the real part of, in 2D math, you can use that symbol. Imaginary part, in 2D math, you can use that symbol. ABS is the command for the absolute value or the modulus or the magnitude. You can use two strokes around the quantity to get the magnitude. So I want to do some examples in Maple. And in order to make these examples easier to implement, here are the initializations that I made use of. Here's where I did the alias. Alias arg equals argument. Here's where I changed the imaginary unit. Interface imaginary unit equals I. Here's where I defined the function n1 of z. And I simply use the context panel. I think I can show you that here. Context panel. Assign function. So that takes care of the machinery of making this assignment. I did the same thing here. N2, assign as function. Context panel. Here, for some reason or other, I used the arrow notation. N3, I did that for N4. And for K, I went back and I used assign function. So these are the initializations that allow the examples to work. Well, we have 7 laws to consider, and I have 7 examples. First example is log of e to the z, and I picked this for z. And what we want to compute is log of e to the z. If you simply say log of e to the z is z, you will get this number. But if you use Maple here, which has the principal value of the complex logarithm built in, log of e to the z is this number. You'll notice this is the adjustment factor. If you use n1 or if you use k, well, we discovered that they're both the same. You get the correct answer, because here's the adjustment, 2 pi I in both cases. N1 and k are both 1. Well, that's the kind of example that illustrates that you sometimes have to make an adjustment on these laws to make them valid in the complex plane. So this is just some computation, and I'm looking for insight. Kept pondering what makes this jump off the page at me. What's really happening here? Well, I ended up drawing this diagram. I drew this diagram. This is z. So this arrow represents the vector to z. This is e to the z. It turned out I didn't really need that. This is log of e to the z. So this is the right answer. That's why I did it in green. This is 2 pi I. The sum of the blue and the black gives you the green. So you've got to add enough on this axis to pull this vector up to here. Well, computationally, here's z, here's log of e to the z, and vectorially, this is z minus 1 minus 4. You've got to add something to this to make it turn out to be the right answer, which we see to be minus 1, 2 pi minus 4. So you have this equation across here and across here. Minus 1 here, minus 1 here, so A is 0. Minus 4 here, so B is 2 pi. And that's why this is 2 pi I. Well, that made me feel a little bit better, that I could actually see where these angles are and what's happening to the vectors that represent these complex numbers that move z to log of e to the z. Well, for a second example, we're looking at log of z to the w. So I need a z and I need a w. And I'm looking at log of z to the w. Well, I went to floating point numbers because the exact numbers, the exact quantities, they're kind of difficult to spot what's really happening. So I floated W log Z. And that's the incorrect answer. And you can see here what you would get. If I take log of Z to the W using Maple and float that, this part's the same, but this part's not. So an adjustment has been made. Well, this is the Panisi adjustment, and this is the unwinding number adjustment. Both of those give the correct value. N2 is what you need for the Panisi adjustment, and K is what you need for the unwinding number adjustment. And you can see here where the W fits into K, it's K of W log Z. So numbers, they work out either N2 or K. I think K is simpler. And then we'll see if we can get some insight into what's happening here. So as we did in example 1, represented the complex numbers as vectors, try to get some insight into how these adjustments take place. So this is the incorrect W log Z, this naive. This is the adjustment vector. The sum of these two produces the correct answer, again in green, for log of Z to the W. And here would be the vector arithmetic. W log Z, real part. W log Z, imaginary part. You've got to add something to that in order to get the correct stuff, real part, imaginary part. Well, you can see here log 17, arctangent 4, arctangent 4 minus pi. So A is 0. 2 arctan 4, 2 arctan 4, log 17 over 2, log 17 over 2. So B is 2 pi. And that's why this is 2 pi I and why the correction factor works. So example 3, we look at the log of a product. So we need a Z1 and a Z2, and we are computing the log of that product, Z1 times Z2. And this is the incorrect answer if you just simply take the sum of the logs. And again, we're working floating point arithmetic. Log of the product in Maple, which should be the correct answer, floated, you can see the imaginary part is going to be different. If you take the sum of the logs and you use the Panisi adjustment, you need N3. Well, you will get the right answer. If you use the unwinding number correction, of course you will get the right answer. In both cases, the correction factor, either it's N3 or the unwinding number of the sum of the logs, comes out to be 1. Well, can we get some graphical insight as we've just done in the previous 2 examples? This is the incorrect log Z1 plus log Z2. This is the naive approach. This is the correct value, log of the product computed via Maple, so you get the right answer. This is the adjustment. Sum of these two, the blue and the black, give you the green. And here's the arithmetic that goes along with it. This is the incorrect. You've got to add something to that to get the correct. So log of 85 over 2, log of 85 over 2, so A is going to be 0. Here you have minus pi minus arctan 9 halves. Here you have pi minus 9 arctan of 9 halves. So B is going to be this pi brought over, and this pi you get 2 pi. That's why this is 2 pi I. So again, this little picture makes the arithmetic sort of come alive, and it's a bit more satisfying than just throwing some numbers around. So having done log of a product, we're going to do log of the quotient. So we need two z's, z1 and z2, and we're looking at log of the quotient. This is the incorrect. If you just write down the difference of the logs, this is what you'll get. If you do it in Maple, so you get the right answer, log of the quotient. Real part's okay, but it's the imaginary part that's not. This is the Panisi adjustment, N4, and if you look at what the value of N4 is, it's -1. This is the unwinding number adjustment. It also is -1, and clearly they give you the correct answer. Well, can we get some graphical insight as we've been doing? Let's try that. This is the incorrect, just the difference of the logs. This is the correct, log of the quotient computed in Maple, so you get the right answer. It's in green. Notice that the correction factor, K or N4, they're -1, which means minus 2 pi I. So this is minus 2 pi I, and it's the sum of the blue and the black that has to give you the green. And here is the arithmetic that goes along with it. This is the incorrect, log minus log. So the difference of the logs gives you this. You have to add something to get the correct, which is this. And you can see here that A is going to be 0, and you have 7/4 pi minus arctan of a half, and here you have minus arctan 3. Well, now you have a problem of sorting that out, so let's get Maple to do that. Arctan of a half, if you bring that over, minus arctan 3, then you bring this over, minus 7 pi over 4. If you hit it with a simplify, it turns out to be minus 2 pi. So there is your B, minus 2 pi. That's why this blue arrow points downwards here. Black and the blue gives you the green. Now these first 4 examples parallel the 4 laws that we called elementary. When you get down to the last 3 laws, the correction factor is no longer additive. It's multiplicative. So things are going to be slightly different. So I'm looking at a product raised to the W power. So we need 2 numbers, Z1, Z2, to multiply together, and a W to be the exponent. So we're computing the product raised to the W. Incorrect way to do this is to bring or distribute the W to both Z1 and Z2. And notice what you get for an answer if you do that. Big number here, very surprising. And we do it in Maple till we get the right answer, and you see the real and imaginary parts are much smaller. This is the correction factor using the Panisi approach. It's a product. It's an exponential, 2 pi I. W appears up in there, and you need N3. If you use the unwinding number approach, it's e to the 2 pi I W times the winding number. Now, in each instance here, we see that either N3 or the unwinding number, it's 1. All you have to remember here with the unwinding number is what is the argument, and don't forget that there's a W here. Now remember, the correction factor is multiplicative, it's not additive. So when we're looking for additional insight, we've got to do some numbers rather than draw some pictures. So let's look at the argument of the incorrect way of going about this, the naive way of going about this. Distribute W to the 2 factors. There's the argument. Look at the argument of the correct way of doing this. You multiply first, then you raise it to the power. The argument is the same, so the problem is not in the argument. So let's look at the modulus. Here we have distributed W incorrectly to the 2 factors. Take the modulus. There's where that big number is coming from. Now to do it correctly, take the modulus. Do not distribute to W. Take the modulus. Much, much smaller. Let's look at the correction factor. E to the 2 pi I, now W, and K or N3, they're 1, so they're not showing up here because it's 1. 2 pi I W. So e to the 2 pi I W is e to the minus 2 pi. Look up here at W. W is 1 plus I, and you are multiplying that by an I. So you get I minus 1. There's the minus 1 is there. E to the 2 pi I is 1. And that's why this turns out to be e to the minus 2 pi. So here is the incorrect distribution of the exponent to the factors, but we have compensated by e to the minus 2 pi. And now we looked at the modulus, and the modulus here matches the modulus here. In other words, this is 1 over approximately e to the 6th. Now, e to the 6th is a big number. 1 over e to that big number is a small number. That's what chops this thing down to something smaller. And so by looking at some of these numbers, we get a better sense of how this multiplicative corrective factor behaves. Now, here's a caution, and this came to me after a little bit of experimenting. When we looked at this W and we multiplied it by I, too many nice things happened. And I said to myself, what happens if W is not all full of integers? And so I picked a different W, 0.6 minus 0.7i. And I did the computation over again. So incorrect distribution of the exponents, you get this thing. Correct distribution of exponents, I get this thing. Nothing matches. Incorrect distribution of the exponents using the Panisi correction factor, I get agreement with what Maple does. And if I use the unwinding number version of the correction factor, I get a match with what Maple does. And in each instance, the correction factor here, N3, here it's K, they're 1. So let's look at the correction factor, e to the 2 pi I W, for this W here. You notice it doesn't collapse to something nice like e to the minus 2 pi. What is the argument of the correction factor? This is the argument of that correction factor, e to the 2 pi I W. Remember, either K or N3 is 1, so you get 2 pi I W. What is the magnitude of the correction factor? Well, that's 81. Now, I drew two vectors, black and green. This is the bad one, this is the good one. Incorrect distribution of the exponent, I get this vector. Correct distribution of the exponent, which is don't distribute it, get this green one. And what is the angle between these two vectors? Well, I made a vector here, real part of the black, imaginary part of the black. And here's the other vector, real part of the green, imaginary part of the green. And I calculated the angle between those two vectors, 2.5. Now this is minus 2.5. This is a question of whether I went this way or this way. But the magnitude of that angle agrees. So the caution here, and I had to double back and think about this. If W is a complex number, not just nicely packed with integers, you can expect differences in here, in these quantities, for the correction factor that don't simplify the way they did in the previous example. The behavior in example 6 is going to be a lot like we saw in example 5. Here we have the quotient of two complex numbers raised to a complex power. Two complex numbers, and you'll notice the W is nice. It's got integers, 1 plus I. So what we're computing is the quotient raised to the W power. This is the incorrect way to do it. Distribute the exponent. Well, we get this answer. If you do it in Maple, Maple will do it properly, and it will give you a different answer. Correction factor, according to Panizzi, this is this N4 thing. Correction factor using the unwinding number. In each case, the N4 and the unwinding number, -1. So e to the 2 pi I w, and there'll be a -1, the correction factor here, -1. That w is going to make this correction factor very simple, as we saw in example 5. However, in each instance, Maple, Panizzi correction factor, unwinding number correction factor, they all come out to be the same. So digging into these numbers a little bit more computationally to see what's happening. Incorrect distribution of the exponent, you get the argument. Correct distribution of the exponent, which is don't distribute it, you get the same thing, the same argument. So you look at the modulus. Incorrect distribution of the exponent, this is the modulus. Correct distribution of the exponent, which is don't distribute it, modulus is considerably larger, multiplicatively larger. The correction factor, which is again a multiplicative correction factor, turns out to be e to the minus 2 pi I w, because k is -1, and w has got these nice integers in it, and it turns out to be e to the 2 pi. And so if you incorrectly distribute the exponent but compensate with an e to the 2 pi, then you get the correct value. So when I kept seeing this correction factor turn out to be something nice like e to the 2 pi or e to the minus 2 pi, I kept shaking my head saying, why is that happening? And then that's when I realized it was because of this w that I had picked. So pick a different w. Pick a w like 0.6 minus 0.7i and run through those numbers again. So this is what we're looking at. Quotient raised to the w. Incorrect distribution of the exponent, you get this, which is not the right answer. If you do it properly, let Maple do it, this is the correct answer. And if you do it incorrectly but compensate with the Panizzi compensation, you get the correct answer. And if you do it incorrectly but compensate with the unwinding number, you get the correct answer. So whether it's N4 or K, it's 1. So let's take a deeper look at those numbers. This is the correction factor, 2 pi I w, because K is 1, so it's e to the 2 pi I w. Notice it does not collapse to like e to the 2 pi. The argument of the correction factor, there it is. The magnitude, there it is, big number. So I drew two vectors. Black vector is the incorrect version. So you just distribute the w to the factors in the quotient. That's this black vector. If you do it correctly, that's the green vector. You get this. And what is the angle between those two vectors? So make an angle, real part of the black, imaginary part of the black, make a vector, real part of the green, imaginary part of the green. Get the angle between them, 2.51. Here it's 2.51, sign difference. So it's a question of how I'm measuring, this way or this way. And so that was enlightening because it made me realize that getting a nice correction factor like e to the 2 pi is a function of this w that I picked. And so for our seventh and final example, we look at the law z to the v all raised to the w. And so we have a z, a v, and a w. And what we're looking at is the computation of z to the v to the w. If we do it incorrectly and multiply the two exponents, I will get this answer. There's nothing here really to tell me that it's not the right answer. If we let Maple do it, Maple will do it correctly. It will compute z to the v first, and then it will raise that to the w power. We get this answer. If we do it incorrectly, but compensate with the Panizzi compensation, we get the correct answer because these match. And if we do it incorrectly but compensate with the unwinding number compensation or corrector, we get the same answer. So these three are all the same, so they are correct. And notice that here n2 is the Panizzi way, minus 1, the unwinding number, minus 1. And so we dig into these numbers just a bit, as we did before. I will look at the argument of the incorrect way of doing this. Multiply the v and the w. We get this number. And if we do it correctly, take the argument. First you do z to the v, then you raise that to the w. You get the same argument. So the problem is not in the argument. So let's look at the magnitude. What is the magnitude of the incorrect way of doing it? It's a small number. The modulus of the correct way to do it is several orders of magnitude bigger. And if you look at the correction term, the k or the n2 is negative 1, so it's e to the minus 2 pi I w. But remember, this is a very special w. It's 1 plus I. And it comes out to be e to the 2 pi, and that's what I kept looking at and saying, why is that correction factor coming out so nice? Is it always going to be quite so nice? And if we do it incorrectly, we'll put in that correction factor, e to the 2 pi, take the modulus, and the modulus here agrees with the modulus here. The question is, why does that correction factor here turn out to be e to the 2 pi so nice? It's because of the w we picked. So as we did earlier, we investigate the role of w in producing such nice correction factors. So we take w to be 0.6 minus 0.7 I, run through the computation again. If you distribute the exponents or multiply the exponents incorrectly, you get this answer. There's no way of telling whether that's right or wrong or not. So here I've done it in Maple, correct use of parentheses and so forth. You get this answer. Incorrect procedure here, correction factor a la Panizzi, you get the same thing that Maple got. And if you do the correction factor using the unwinding number, again it agrees with Maple. So the unwinding number minus 1 and 2 is minus 1. Let's take a look at this e to the minus, because of this minus sign, minus 2 pi I w. See, that's where that w comes in. If it's not all packed with integers, then the argument is this. The incorrect version is this black vector here, and I clearly scale these vectors so they would fit on the page. The correct version is in green, that's this one. And the angle between I calculate by saying, okay, make a vector, is the black one, so you get the real part and the imaginary part are the components to that vector. Real part of the green one, which is the correct one, imaginary part. and you compute the angle between 2.5, 2.5, the angles agree. So the multiplicative correction factor has this correct argument, which is a rotation in the complex plane. And that's where that angle fits in. So, interesting collection of examples. It took several passes through here to finally get a handle on how these correction factors were behaving. If anybody wants a copy of this worksheet, they should contact me by email, and let me give you the email address. rlopez at maplesoft.com. Send me an email. That way I have a way of getting a copy of this worksheet back to you. Happy to share this with you. It'll save you some time if you wanted to poke around and explore these rules of logarithms and exponents in the complex plane.